Welcome to ZzScience. Before we begin, allow your body to relax, your breathing to slow, and your mind to gently drift. Tonight, we explore science, quietly, calmly, and without urgency. There is nothing you need to do, only listen. In the beginning, there was something we might call nothingness, though even this word fails to capture the profound absence that existed before existence itself took form. Imagine, if you will, a state so completely empty that even the concept of emptiness had no meaning. A condition where time itself had not yet begun to flow, where space had not yet unfolded its dimensions, where the very laws of physics that govern our reality lay dormant, waiting in some incomprehensible potential state for the moment of their awakening. This was not a darkness, for darkness implies the absence of light, and light had not yet been conceived. This was not silence, for silence requires the possibility of sound, and sound waves needed matter and space through which to travel, neither of which existed. This was a state beyond our ability to truly comprehend, a realm where our language breaks down and our imagination falters, where even the greatest minds throughout human history have struggled to find adequate words or concepts to describe what might have been. Yet within this profound nothingness, within this absence of everything we know and understand, there existed a kind of quantum foam, a seething ocean of possibility, where virtual particles flickered in and out of existence in timescales so brief that they defy our ordinary understanding, where the energy of the vacuum itself contained within it all the potential for everything that would ever be. The universe as we know it, with all its vast expanses of space filled with countless galaxies, each containing hundreds of billions of stars, with planets orbiting those stars, with the very atoms that make up our bodies and everything around us. All of this emerged from a single point of infinite density and infinite temperature. A singularity where all the mass and energy that would eventually spread across billions of light years of space was compressed into a region smaller than the smallest subatomic particle we can imagine. The mathematics that describe this moment become strange and wonderful, filled with infinities that signal the breakdown of our theories, suggesting that at this most fundamental moment, space and time themselves were woven together in ways that our current understanding cannot fully penetrate. Quantum mechanics, that strange and beautiful theory that governs the behavior of the very small, and general relativity, Einstein's elegant description of gravity as the curvature of space-time, both reach their limits here, at this boundary where the universe begins, and physicists dream of a theory of quantum gravity that might finally reveal the true nature of this primordial instant. For reasons that remain among the deepest mysteries in all of science, this singularity, this infinitely dense point of pure potential, began to expand. Not into space, for space itself was being created in this expansion, but rather space itself was expanding, unfurling, blossoming outward in all directions simultaneously. This moment, which we have come to call the Big Bang, though it was neither big in the sense of being large, for it started infinitesimally small, nor a bang in the sense of an explosion into empty space, for there was no space for it to explode into, mark the beginning of everything we can observe, measure, and study. In the first unimaginably brief instant, a period of time so short that compared to a single second, it would be like comparing the width of a single atom to the entire visible universe. Something extraordinary happened. The universe underwent a period of exponential expansion called cosmic inflation, where space itself expanded faster than the speed of light, doubling in size over and over again in a cascade of growth so rapid that a region smaller than a proton swelled to astronomical proportions in a fraction of a heartbeat. This inflationary epoch, lasting perhaps from 10 to the minus 36 seconds to 10 to the minus 32 seconds after the initial moment, solved several puzzles that had troubled cosmologists. It explained why the universe appears so uniform in all directions, why distant regions of space that could never have been in contact with each other nonetheless have almost exactly the same temperature and properties, because they were once close together before inflation stretched them apart. It explained why space appears to be flat rather than curved, because even if the universe had some curvature initially, the rapid expansion would have stretched that curvature out until it became imperceptible, much like the surface of a balloon appears flat if you inflate it to an enormous size. And perhaps most wonderfully, it explained where all the structure in the universe came from, all the galaxies and galaxy clusters, and the vast cosmic web of matter. Because quantum fluctuations in that initial tiny region, tiny random variations in the density of energy, were stretched by inflation to cosmic scales, providing the seeds from which all structure would later grow. As this period of inflation came to an end, the energy that had been driving the expansion, the energy of the inflaton field that had been pushing space apart, was converted into a bath of radiation and matter, filling the universe with particles and antiparticles, with photons of light, with quarks and leptons, and all the fundamental constituents of matter. The universe at this moment was unimaginably hot, with temperatures reaching perhaps 10 to the 27th degrees Kelvin, so hot that no atoms could form, so hot that even protons and neutrons could not yet exist, so hot that matter existed only in its most fundamental form, as a seething plasma of quarks and gluons, the basic building blocks from which protons and neutrons would later be assembled. This quark-gluon plasma, this primordial soup of fundamental particles, filled all of space, which, though rapidly expanding, was still incredibly dense, with energies and temperatures that we can only recreate in our most powerful particle accelerators for the briefest instants. The photons, the particles of light that were being created and absorbed and scattered in this cosmic furnace, could not travel far before colliding with charged particles. And so the universe at this early time was opaque, a glowing fog where light could not freely stream across space, but was constantly bounced and scattered in every direction. Quarks and antiquarks were constantly being created from pure energy, and then annihilating back into energy in a continuous dance of creation and destruction. But there was a slight asymmetry, a tiny imbalance, where for every billion antiquarks, there were 1,000,000,001 quarks. And this small difference, this barely perceptible excess of matter over antimatter, would prove crucial, for it meant that when the universe cooled enough that quarks and antiquarks could no longer be created from the ambient energy, and all the existing ones annihilated with each other, there would be a small remainder, a residue of matter left over, and this residue would become everything we see today. As the universe continued to expand, it also continued to cool, and after about 1 microsecond, a millionth of a second after the beginning, the temperature had dropped to around 10 to the 13th degrees Kelvin, cool enough that quarks could bind together to form protons and neutrons, the particles that would eventually make up the nuclei of atoms. This transition from quark-gluon plasma to hadronic matter, from free quarks to bound protons and neutrons, marked an important threshold in the universe's evolution. The strong nuclear force, one of the 4 fundamental forces of nature, was now able to confine quarks within these composite particles, and the character of matter changed from a plasma of fundamental particles to a plasma of these slightly more complex composite objects. Still, the universe was far too hot for atoms to form. Still, the photons of light scattered constantly off charged particles. Still, space was filled with this opaque, glowing fog. But the first steps toward the matter we know today had been taken. During the next few minutes, between about 1 second and 20 minutes after the Big Bang, the universe went through a crucial process called Big Bang nucleosynthesis, where the protons and neutrons that had formed began to fuse together to create the first atomic nuclei. At first, when the temperature was still above 1 billion degrees Kelvin, neutrons were being converted into protons and protons into neutrons through the weak nuclear force, maintaining an equilibrium between these two types of particles. But as the temperature continued to drop, neutrons became less abundant relative to protons, because free neutrons are unstable and decay into protons with a half-life of about 15 minutes, and at lower temperatures, they could not be produced as easily from protons. By the time the temperature had dropped to about 1 billion degrees, roughly 1 neutron remained for every 7 protons, and conditions were just right for nuclear fusion to begin. In this primordial furnace, protons and neutrons began combining to form deuterium, a heavy form of hydrogen with 1 proton and 1 neutron in its nucleus. And then deuterium nuclei fused with protons to form helium-3, or with each other to form helium-4, the common form of helium with 2 protons and 2 neutrons. Trace amounts of lithium and beryllium were also formed in these first minutes. The process was remarkably efficient at creating helium, with nearly all available neutrons ending up bound in helium nuclei, and this led to a universe where about 3/4 of the ordinary matter was hydrogen, the simplest element with just a single proton, and 1/4 was helium, with only tiny traces of heavier elements. This ratio of hydrogen to helium, forged in the first minutes after the Big Bang, would remain essentially unchanged for hundreds of millions of years, and it matches beautifully with what we observe today in the oldest stars and gas clouds in the universe, providing one of the strongest pieces of evidence for the Big Bang theory itself. After Big Bang nucleosynthesis ended, about 20 minutes into the universe's history, the composition of matter was essentially fixed, but the universe was still far too hot for atoms to form. The nuclei that had been created, mostly hydrogen and helium, remained separate from electrons, existing as a plasma of charged particles. Photons continued to scatter off these charged particles, keeping the universe opaque, a glowing sea of light and matter mixed together. For hundreds of thousands of years, the universe continued to expand and cool, its temperature dropping gradually, its density decreasing, but remaining in this plasma state, this ionized condition where electrons roamed free rather than being bound to nuclei. The photons and matter were in thermal equilibrium, constantly exchanging energy through collisions, and the spectrum of light followed what is called a blackbody curve, the characteristic distribution of wavelengths emitted by an object at a particular temperature. Throughout this long epoch, lasting from about 20 minutes to roughly 380,000 years after the Big Bang, the universe was remarkably smooth and uniform, with only tiny variations in density from one region to another, variations that had been imprinted during the inflationary epoch and stretched to cosmic scales. These variations, though small, were crucial because they represented regions that were slightly denser than average, with a bit more matter and energy than their surroundings. And these denser regions had slightly stronger gravity, which would eventually allow them to pull in more matter and grow into the galaxies and galaxy clusters we see today. But for now, in this plasma epoch, the pressure of radiation prevented these density variations from growing, keeping the universe remarkably uniform and smooth. Then, when the universe had expanded enough and cooled enough that its temperature had dropped to about 3,000 degrees Kelvin, something remarkable happened. At this temperature, electrons finally had low enough energies that they could be captured by atomic nuclei, particularly hydrogen and helium nuclei, without being immediately knocked free again by high-energy photons. This process, called recombination, though it is a misleading name since the electrons and nuclei had never been combined before, transformed the universe from a plasma of free charged particles into a gas of neutral atoms. And with this transformation, the universe suddenly became transparent, because neutral atoms interact much more weakly with light than charged particles do, and photons could finally travel freely across space without being constantly scattered. This moment, when the fog cleared and the universe became transparent, released the light that had been trapped in the plasma, sending it streaming across space in all directions. And this ancient light, cooled by the expansion of the universe from visible wavelengths to microwaves, still fills the universe today as the cosmic microwave background radiation, a faint glow coming from every direction in the sky, carrying information about the state of the universe at this early time. The cosmic microwave background, discovered accidentally in 1964 by Arno Penzias and Robert Wilson, who were trying to eliminate a persistent noise in a radio antenna and eventually realized they were detecting the primordial radiation from the Big Bang itself, is one of the most important sources of information we have about the early universe. By measuring tiny variations in the temperature of this radiation across different parts of the sky, variations of only a few parts in 100,000, astronomers can map the density fluctuations that existed at the time of recombination, seeing the seeds from which all cosmic structure would grow. The pattern of these fluctuations tells us about the composition of the universe, about how much ordinary matter it contains, how much dark matter, how much dark energy, about the geometry of space, about the rate of expansion, about conditions in the first moments after the Big Bang. It is a baby picture of the universe, showing us what it looked like when it was only 380,000 years old. And from this picture, we can trace both backward to understand how the universe began, and forward to understand how it evolved into the magnificent cosmos we see today. After recombination, after the universe became transparent and neutral atoms formed, a long period began that astronomers poetically call the Cosmic Dark Ages. A time when the universe contained no sources of light, no stars yet shone, no galaxies had yet formed, and space was filled only with neutral hydrogen and helium gas, slowly collapsing under its own gravity into the denser regions that had been seeded by those primordial fluctuations. This was not truly a dark time, for the cosmic microwave background still filled space with light. But it was a time without discrete sources, without the brilliant points of light that would come to define the cosmos. The temperature continued to drop as the universe expanded, falling below the freezing point of water, though there was no water yet in the universe, no oxygen having been created, falling eventually to temperatures colder than ice, colder than any natural environment on Earth, as space grew larger and larger, and the matter within it spread thinner and thinner. But while the universe appeared dark and quiet, processes were underway that would transform it. The regions of slightly higher density, where a bit more matter had accumulated, were pulling in more matter through their stronger gravitational attraction. Hydrogen and helium gas was flowing toward these density peaks, falling inward, forming larger and larger clouds. The structure of the universe was beginning to emerge, though it would not become visible for hundreds of millions of years. These collapsing clouds of gas grew denser and hotter as gravity pulled them together, converting gravitational potential energy into heat, warming the centers of the clouds, even as the expansion of the universe cooled the gas between them. Slowly, over tens of millions of years, then hundreds of millions of years, these clouds fragmented and condensed, forming smaller, dense clumps within larger structures, creating a hierarchy of matter from the largest scales down to smaller and smaller regions. The Dark Ages lasted for perhaps 100 million years, perhaps 200 million, the exact timing still uncertain and a subject of ongoing research. But eventually, in the densest regions where the most matter had accumulated, the collapsing clouds of gas became so compressed and so hot that a new kind of physics began to operate. In the cores of these clouds, where pressures and temperatures had climbed to extremes, where matter had been squeezed by gravity into tighter and tighter configurations, the nuclei of hydrogen atoms, which are simply protons, began to collide with enough energy to overcome the electric repulsion between positively charged particles and fuse together, joining to form helium and releasing tremendous amounts of energy in the process. This nuclear fusion, the same process that had occurred in the first minutes after the Big Bang, but now rekindled in these dense knots of matter, began to generate light and heat, and the first stars ignited, burning like beacons in the darkness, ending the cosmic dark ages and beginning what astronomers call the epoch of reionization. These first stars, born from clouds of pure hydrogen and helium, with no heavier elements to speak of, were likely very different from the Sun and other stars we see in our modern universe. Without heavier elements, without metals, as astronomers call anything heavier than helium, the gas could not cool as efficiently as it can today, and this likely meant that the first stars were much more massive than typical stars now, perhaps tens or even hundreds of times the mass of the Sun. These massive stars would have been incredibly hot and luminous, burning brilliant blue, pouring out enormous amounts of ultraviolet light, living fast and dying young, exhausting their nuclear fuel in only a few million years, rather than the billions of years that smaller stars like our Sun can sustain. Their intense ultraviolet radiation began to ionize the neutral hydrogen gas around them, creating bubbles of ionized plasma surrounding each star or cluster of stars. Bubbles that grew and merged as more and more stars formed, gradually reionizing the entire universe and transforming it once again from neutral atoms back to a plasma, though a much more diffuse plasma than had existed before recombination. The formation of the first stars marked a fundamental change in the universe, for these stars were not just sources of light, but also cosmic alchemists, factories where heavier elements were forged. In the cores of these stars, hydrogen fused into helium, helium into carbon and oxygen into neon, magnesium and silicon, building up heavier and heavier elements through the fusion process. The most massive of these first stars, living only a few million years before exhausting their fuel, died in spectacular supernova explosions. And in those explosions, in the intense heat and density of the collapsing stellar core, even heavier elements were created, including iron, gold, uranium, and all the elements heavier than iron that cannot be formed by normal stellar fusion. These supernovae scattered the newly created elements into space, enriching the primordial hydrogen and helium with heavier atoms. And this enriched gas would be incorporated into the next generation of stars, creating a slow buildup of heavy elements as more and more stars lived and died and returned their processed material to the cosmos. As the first stars formed, they did not appear in isolation, but tended to cluster together in small groups, drawn together by gravity into associations that would grow into the first galaxies. These early proto-galaxies were much smaller than typical galaxies today, containing perhaps millions or tens of millions of stars, rather than hundreds of billions. And they were irregular in shape, chaotic and turbulent, still actively forming stars from their gas supplies, still being shaped by the violent deaths of their most massive stars. Over time, these small proto-galaxies began to merge with one another, coming together under mutual gravitational attraction, colliding and coalescing, building up larger and larger structures in a process that continues to this day. Galaxy formation was not a single event, but an ongoing process, a hierarchical assembly where small structures merged to form larger ones, where the building blocks of galaxies came together gradually over cosmic time. The distribution of these early galaxies was not random, but reflected the underlying distribution of matter in the universe, which itself was determined by those primordial density fluctuations from the inflationary epoch. Galaxies formed preferentially in regions where dark matter had accumulated. For dark matter, that mysterious substance that makes up about 85% of all matter in the universe, but does not emit, absorb, or reflect light, had been clustering under its own gravity since recombination, forming a scaffolding, a cosmic web of filaments and nodes, along which and at which ordinary matter could accumulate and form galaxies. This cosmic web, revealed in modern surveys that map the positions of millions of galaxies, shows a remarkable structure, with galaxies strung along filaments that connect massive clusters, surrounding vast empty voids where few galaxies exist, creating a pattern that resembles a three-dimensional spiderweb or foam stretching across the entire observable universe. The largest concentrations of matter, where many filaments intersected and where gravity was strongest, became galaxy clusters. Gravitationally bound collections of hundreds or even thousands of galaxies, along with enormous amounts of hot gas and dark matter. These clusters, the largest bound structures in the universe, grew over billions of years as more and more galaxies fell into them, as smaller groups merged with larger ones, as the cosmic web channeled matter along filaments into these massive accumulations. The hot gas in clusters, heated to tens of millions of degrees by the gravitational energy of infalling matter, emits X-rays that we can detect with space-based telescopes, revealing the distribution of ordinary matter in these systems and complementing observations of the galaxies themselves and measurements of the dark matter through gravitational lensing, where the cluster's gravity bends the light from background galaxies, allowing astronomers to map the total mass distribution. As galaxies formed and evolved, they developed a variety of shapes and structures. Some galaxies, through a combination of mergers, gas accretion, and internal processes, developed into majestic spiral galaxies with flattened, rotating disks of stars and gas, often with beautiful spiral arms where star formation is particularly active and which are traced by bright young stars and glowing gas clouds. These spiral arms are not fixed structures, but rather density waves, regions where the density of stars and gas is temporarily enhanced as material moves through them, triggering star formation and creating the bright appearance. Other galaxies, often formed through major mergers where two comparable-sized galaxies collided and coalesced, became elliptical galaxies, smooth, featureless systems with stars moving on random orbits rather than the ordered rotation of spiral galaxies, containing mostly old red stars with little ongoing star formation and relatively little gas and dust remaining. Still other galaxies remained irregular, without clear structure or symmetry, often rich in gas and actively forming stars, shaped by recent interactions or mergers or by their position in the cosmic web. At the centers of most large galaxies, in the very heart of these vast stellar systems, something extraordinary lurks. Supermassive black holes, objects containing millions or even billions of times the mass of the Sun, compressed into a region smaller than our solar system, sit at the centers of galaxies, including our own Milky Way. The formation of these supermassive black holes remains one of the great puzzles in astrophysics, for we observe them at very early times in the universe's history, less than 1 billion years after the Big Bang, when there should not have been enough time for them to grow to such enormous masses through the ordinary process of accreting matter. Perhaps they formed from the collapse of supermassive stars in the early universe, or from the direct collapse of gas clouds, or through the merger of many smaller black holes, or through some combination of these processes. However they formed, these black holes play a crucial role in galaxy evolution, for when matter falls toward them, it heats up and emits tremendous amounts of energy, creating what we call active galactic nuclei, or quasars, among the most luminous objects in the universe, visible across billions of light-years of space. The energy released by these active supermassive black holes can blow gas out of galaxies, regulating star formation by removing the raw material from which stars form, creating a feedback mechanism that links the growth of the black hole to the evolution of its host galaxy. Observations have revealed a tight relationship between the mass of the central supermassive black hole and properties of the galaxy that surrounds it, such as the mass of the central bulge or the velocity dispersion of stars, suggesting that black holes and galaxies grow and evolve together in an intertwined cosmic dance. The most luminous quasars in the early universe, shining with the light of trillions of suns, help to reionize the universe completely, their ultraviolet and X-ray radiation reaching far beyond their host galaxies to ionize neutral hydrogen in intergalactic space, contributing to the transformation of the cosmos from neutral to ionized that had been started by the first stars. Our own galaxy, the Milky Way, formed through this same general process of hierarchical assembly, beginning as small protogalactic clumps that merged together in the early universe. The oldest stars in the Milky Way, found in the stellar halo that surrounds the main disk, in globular clusters that orbit the galaxy like a swarm of bees, have ages of around 13 billion years, meaning they formed less than 1 billion years after the Big Bang, when the universe was still very young. These ancient stars, with very low abundances of heavy elements, are relics of the early stages of galaxy formation, witnesses to the assembly of our galaxy. Over billions of years, the Milky Way continued to grow through mergers with smaller galaxies, and even today we can see the remnants of past mergers, streams of stars that trace the paths of disrupted dwarf galaxies. And we observe dwarf galaxies like the Large and Small Magellanic Clouds that are currently being torn apart by the Milky Way's tidal forces. The Milky Way has a structure typical of large spiral galaxies, with a central bulge containing mostly old stars, a thin, rotating disk with beautiful spiral arms traced by young blue stars and pink emission nebulae where star formation is ongoing, and a more diffuse, thick disk and stellar halo containing older stars on more random orbits. The disk is embedded in a much larger dark matter halo, roughly spherical and extending far beyond the visible galaxy, containing most of the galaxy's mass, but completely invisible except through its gravitational effects. Our solar system resides in the disk, about 26,000 light-years from the galactic center, orbiting around the center at a speed of about 200 kilometers per second, completing one full orbit roughly every 230 million years. The stars we see in our night sky are almost all members of the Milky Way, our cosmic home, though a few of the fuzzy patches visible to the naked eye are actually other galaxies, most notably the Andromeda Galaxy, our nearest large galactic neighbor. The Milky Way is part of a small cluster of galaxies called the Local Group, which includes Andromeda, the Triangulum Galaxy, and about 50 smaller dwarf galaxies, all bound together by their mutual gravitational attraction. The Local Group itself is part of a larger structure called the Virgo supercluster, or in more recent terminology, the Laniakea supercluster, a vast cosmic structure spanning hundreds of millions of light-years and containing tens of thousands of galaxies. But even this supercluster is not the end of the hierarchy, for superclusters themselves are arranged along the filaments of the cosmic web, separated by voids, creating structure on the largest observable scales. When we map the distribution of galaxies across the entire observable universe, we see this web clearly, a magnificent pattern of structure that originated from those tiny quantum fluctuations in the first moments after the Big Bang, amplified by inflation, grown through gravitational instability over billions of years, and shaped by the interplay of ordinary matter, dark matter, and dark energy into the cosmos we observe today. Within this grand cosmic structure, in one ordinary spiral galaxy among hundreds of billions, in one ordinary spiral arm, around one ordinary yellow star of moderate size and temperature, the stage was set for the next great chapter in the story of the universe. Our Sun formed about 4.6 billion years ago from a cloud of gas and dust in the Milky Way's disk, a cloud that had been enriched with heavy elements from previous generations of stars, containing not just hydrogen and helium, but also carbon, oxygen, silicon, iron, and all the other elements that would prove crucial for the formation of rocky planets and eventually for life itself. This cloud, perhaps disturbed by a nearby supernova explosion or by the compression from a passing spiral density wave, began to collapse under its own gravity, rotating faster as it contracted, flattening into a disk with a dense central concentration that would become the Sun. In the center of this collapsing cloud, the proto-sun grew hotter and denser as gravity compressed the gas, converting gravitational potential energy into thermal energy, heating the core until, after perhaps 50 million years of contraction, the temperature reached about 10 million degrees Kelvin, hot enough for hydrogen fusion to begin, and the Sun ignited, becoming a stable main sequence star where it has remained for the past 4.6 billion years, and where it will remain for another 5 billion years or so before its hydrogen fuel begins to run out. Meanwhile, in the disk of gas and dust that surrounded the young Sun, a process was underway that would create the planets, moons, asteroids, and comets of our solar system. The disk, initially composed of the gas and dust that had not fallen into the Sun, was not uniform, but contained local concentrations where material began to stick together. Dust grains, microscopic particles of rock and ice, collided and adhered to one another, gradually building up larger and larger aggregates. These growing bodies, from pebbles to boulders to kilometer-sized planetesimals, continued to collide and merge, sweeping up material from their orbital neighborhoods, growing into planetary embryos, and eventually into the planets we see today. Close to the Sun, where temperatures were high, only rocky materials and metals could condense, and the inner planets formed as small rocky worlds: Mercury, Venus, Earth, and Mars. Farther from the Sun, beyond what is called the frost line, water ice and other volatile compounds could condense, allowing much more mass to accumulate, and the outer planets formed as gas giants, Jupiter and Saturn, and ice giants, Uranus and Neptune, massive worlds with thick atmospheres surrounding rocky cores. Earth formed about 4.54 billion years ago through this process of accretion, countless collisions of smaller bodies building up the mass of our planet over tens of millions of years. The early Earth was very different from the world we know today. Hot and molten, constantly bombarded by remaining planetesimals, its surface a sea of magma, its atmosphere composed of gases released from the interior through volcanic outgassing. Perhaps the most dramatic event in early Earth history was a collision with a Mars-sized body that astronomers have named Theia, which struck the young Earth at an angle, vaporizing much of both bodies. And from the debris cloud that was ejected into orbit around Earth, our moon formed, coalescing from this material over a relatively short time. This collision may have also contributed to establishing Earth's rotation and axial tilt, giving us our day-night cycle and our seasons. Over hundreds of millions of years, Earth cooled, its surface solidifying into a crust, water vapor in the atmosphere condensing into rain that fell and collected in basins to form the first oceans, creating conditions that would eventually allow life to emerge. The bombardment of debris left over from planet formation continued, though gradually decreasing in intensity, and some of this infalling material may have delivered water and organic compounds to Earth's surface, supplementing what was already present. Somewhere in this early ocean, perhaps near volcanic vents on the seafloor, where energy and chemical nutrients were abundant, or perhaps in tidal pools on the shore, or perhaps even delivered from space in meteorites, the first self-replicating molecules appeared, the first sparks of life in a universe that had been preparing for this moment since the Big Bang. For without the heavy elements forged in stars, without carbon and oxygen and nitrogen and phosphorus, without the specific conditions present on a rocky planet in the habitable zone around a stable star, in a galaxy that had been enriched by generations of stellar alchemy. Life as we know it could not exist. Life on Earth began at least 3.5 billion years ago, and perhaps as much as 4 billion years ago, remaining single-celled for most of its history, evolving slowly through random mutations and natural selection, developing photosynthesis which released oxygen into the atmosphere and transformed Earth's environment, eventually giving rise to complex multicellular organisms, to plants and animals, to the vast diversity of life we see today, and ultimately to conscious beings capable of looking up at the night sky and wondering about their place in the cosmos, capable of studying the universe and reconstructing its history, capable of understanding that they are made of atoms forged in the hearts of stars, that their very existence is a consequence of cosmic evolution stretching back to the Big Bang itself. We are, in a very real sense, the universe becoming conscious of itself. Collections of atoms arranged in such a way that they can think and feel and wonder. Star stuff, contemplating the stars. As we look around us today, we see a universe that is about 13.8 billion years old, vast almost beyond comprehension, containing at least 2 trillion galaxies, each with hundreds of billions of stars, stretching across a distance of about 93 billion light-years. For the universe has expanded since the Big Bang and continues to expand today. The expansion is not a movement of galaxies through space, but rather an expansion of space itself, with galaxies embedded in this expanding space like raisins in a rising loaf of bread, each receding from all the others as the space between them grows. This expansion was discovered in the 1920s by Edwin Hubble, who observed that distant galaxies are moving away from us with speeds proportional to their distance, a relationship now known as Hubble's law. And this discovery provided some of the first evidence for the Big Bang theory. For an expanding universe implies that it was smaller and denser in the past, tracing back to that initial moment of extreme density and temperature. Remarkably, we have discovered that the expansion of the universe is not slowing down as we might expect from the gravitational attraction of all the matter in it, but rather it is accelerating, speeding up over time. This acceleration, discovered in 1998 through observations of distant supernovae, implies the existence of a mysterious dark energy, an energy associated with space itself that acts as a kind of anti-gravity, pushing space apart rather than pulling it together. Dark energy makes up about 68% of the total energy content of the universe, with dark matter accounting for about 27%, and ordinary matter, the atoms that make up stars and planets and people, comprising only about 5%. We live in a universe dominated by things we do not yet understand, where the nature of dark matter and dark energy remain among the greatest mysteries in science, but where every observation brings us closer to comprehension, where each discovery reveals new layers of beauty and complexity in the cosmos. The acceleration of the universe's expansion has profound implications for the future. If dark energy continues to drive an accelerating expansion, as all current evidence suggests it will, then the universe will continue to expand forever, growing larger and colder and more diffuse with each passing eon. Galaxies outside our local group are already receding from us, and as the expansion continues, they will move farther and farther away, eventually crossing what is called the cosmic event horizon, beyond which we can never receive light or any signal from them, effectively disappearing from our observable universe. In the far future, beings living in the Milky Way or in the Andromeda galaxy, which will merge with the Milky Way in about 4 billion years to form a single large elliptical galaxy that astronomers have playfully nicknamed Milkomeda, those future observers will see a much emptier universe than we do, with only the galaxies of the local group visible, surrounded by emptiness. the rest of the universe having receded beyond their cosmic horizon. Star formation, which has been ongoing since the first stars lit up hundreds of millions of years after the Big Bang, will not continue forever. Stars form from clouds of gas, and while dying stars return some of their material to space, much of it becomes locked up in stellar remnants, white dwarfs, neutron stars, and black holes, or is blown out of galaxies by stellar winds and supernova explosions. Gradually, over trillions of years, the supply of gas available for star formation will be exhausted, and the era of star formation will come to an end. The last stars will be small red dwarfs, frugal burners of hydrogen that can sustain fusion for trillions of years, far longer than the current age of the universe. But eventually, even these will exhaust their fuel and fade, becoming cold white dwarfs, or perhaps, if they are massive enough, collapsing into black holes. In this far future, in what is sometimes called the degenerate era, lasting from perhaps 100 trillion years to 10 to the 37th years after the Big Bang, the universe will be populated by stellar remnants, dead stars no longer shining, planets that have either been ejected from their stellar systems or orbit cold white dwarfs in eternal darkness, brown dwarfs that never quite achieve the mass needed to ignite fusion, and an increasing population of black holes that have consumed other matter or formed from the collapse of the most massive stars. The temperature of the cosmic microwave background, already cooled to about 3 degrees above absolute zero today, will continue to drop as space expands, approaching closer and closer to absolute zero, creating a universe that is not only dark, but also profoundly cold, where the ambient temperature of empty space is barely distinguishable from the coldest possible temperature allowed by physics. During this degenerate era, occasional flashes of light may still occur when two brown dwarfs collide and briefly achieve enough mass and temperature to ignite fusion, or when white dwarfs in binary systems slowly accrete matter from their companions until they reach a critical mass and explode as supernovae, type Ia supernovae, that today serve as standard candles for measuring cosmic distances, but which in that far future will briefly illuminate an otherwise dark universe before fading back into darkness. These events will become increasingly rare as time passes, as objects drift farther apart due to the expansion of space, and as the probability of collisions decreases, until eventually even these occasional flares cease, and the universe settles into a deep and enduring darkness, punctuated only by the faint glow of Hawking radiation from black holes. Black holes, those regions of space-time where gravity is so strong that nothing, not even light, can escape from within the event horizon, are not truly black, but actually emit a faint thermal radiation, predicted by Stephen Hawking in 1974, due to quantum effects near the event horizon. This Hawking radiation causes black holes to slowly lose mass over incredibly long timescales, evaporating gradually, with the evaporation rate depending on their mass. Small black holes evaporate faster than large ones, and a black hole with the mass of the Sun would take about 10 to the 67th years to evaporate completely, while a supermassive black hole with billions of solar masses would take 10 to the 100 years or more. These timescales are so vast that they dwarf the current age of the universe by factors of trillions of trillions of trillions. Stretches of time so long that they challenge our ability to comprehend them. Yet they are finite, and given enough time, even the largest black holes will eventually evaporate away. The black hole era, when black holes are the dominant massive objects in the universe, will last from perhaps 10 to the 37th years to 10 to the 100 years after the Big Bang. And during this time, the universe will be almost unimaginably empty and dark, with average densities far lower than even the best vacuum we can create on Earth today, with temperatures approaching absolute zero, with distances between objects measured not in light years or megaparsecs, but in scales that require new units to describe, where the observable universe as we know it has long since fragmented into causally disconnected regions that can never influence each other again. In this era, matter as we know it may not be stable, for some theories of physics predict that protons, which we observe to be stable over the current lifetime of the universe and much longer, may eventually decay into lighter particles over timescales of perhaps 10 to the 36th years or longer. And if protons do decay, then even the cold, dead stellar remnants will gradually dissolve, breaking down into lighter particles and radiation, leaving behind only black holes and the diffuse radiation from their decay products. After the black hole era comes what some cosmologists call the dark era, beginning around 10 to the 100 years after the Big Bang, when even the last and largest black holes have finally evaporated away through Hawking radiation, leaving a universe composed only of radiation and the lightest stable particles, photons and neutrinos, and perhaps electrons and positrons, spread across an exponentially expanding space, diluted to almost nothing, with densities and temperatures approaching zero as closely as quantum mechanics will allow. In this final era, the universe will be cold and dark and empty beyond our ability to imagine. A vast expanse of space where the distance between particles is measured in scales larger than the entire observable universe today, where the temperature is infinitesimally close to absolute zero, where nothing changes, where time seems to lose all meaning because there are no processes occurring, no events to mark its passage, just an endless, unchanging emptiness stretching into eternity. Yet even in this far future, quantum mechanics tells us that the vacuum of space is never truly empty, that quantum fluctuations constantly create and destroy virtual particles on the tiniest scales, that there is always some activity, some process, however faint and however meaningless it might seem. Some speculations in theoretical physics suggest that over vast timescales, longer than we can meaningfully express, quantum tunneling might allow spontaneous changes in the vacuum state, possibly even nucleating new inflationary regions that could grow into new universes, new Big Bangs emerging from the quantum foam, creating new cycles of cosmic evolution in an eternal process of creation and destruction. Other theories suggest that the far future universe might be punctuated by extremely rare quantum fluctuations that could spontaneously produce organized structures, Boltzmann brains, or even entire pocket universes, arising from pure chance over timescales so immense that they make the age of our universe seem like an eye blink in comparison. But these speculations take us far beyond what we can observe or test with current science, into realms where our theories become increasingly uncertain and where we must acknowledge the limits of our knowledge. What we can say with confidence is that the universe has a history stretching back 13.8 billion years to the Big Bang, that it has evolved through well-understood physical processes from an initial state of extreme density and temperature to the magnificent cosmos we observe today, and that it will continue to evolve into the future according to the same laws of physics, expanding and cooling, and gradually running down like a clock that was wound at the beginning and is slowly unwinding, not with any final catastrophe, but with a gradual fading into darkness and cold and emptiness that will take longer than mind can conceive. The story of the universe is a story of structure emerging from simplicity, of complexity arising from fundamental laws, of matter and energy organizing themselves into ever more intricate patterns, from the quantum foam of the earliest moments to the elementary particles that formed in the first microseconds, to the atomic nuclei forged in the first minutes, to the atoms that formed after hundreds of thousands of years, to the first stars that lit up after hundreds of millions of years, to the galaxies and galaxy clusters that grew over billions of years, to the planets that formed around later generations of stars, and ultimately to life and consciousness emerging on at least one such planet, possibly on many others. Beings capable of understanding their origins and their place in this grand cosmic story. We are, in a very profound sense, the universe awakening to itself, matter arranged in such a way that it can reflect on its own existence, consciousness arising from unconscious processes through the long chain of cosmic evolution. When we look up at the night sky, we are looking back in time, for light travels at a finite speed and takes time to reach us from distant objects. The light from the moon takes about 1 second to reach our eyes, showing us the moon as it was 1 second ago. The light from the sun takes about 8 minutes, showing us the sun as it was 8 minutes in the past. The light from the nearest star beyond the sun, Proxima Centauri, takes about 4 years, and we see it as it was 4 years ago. When we look at distant galaxies through powerful telescopes, we see them not as they are today, but as they were when their light left them, millions or billions of years ago. And the farthest galaxies we can observe are so distant that their light has been traveling to us for most of the age of the universe, showing us these galaxies as they appeared when the universe was young, when they were still forming their first generations of stars, when they were smaller and more irregular than galaxies today. This ability to look back in time by observing distant objects is one of the great gifts that the finite speed of light gives to astronomy, for it allows us to study the history of the universe directly, to see how galaxies and stars and the universe itself have changed over cosmic time. By comparing nearby galaxies, which we see as they are relatively recently, with distant galaxies, which we see as they were long ago, astronomers can trace the evolution of galaxies over billions of years, watching how they grow through mergers, how their star formation rates change, how their shapes and structures develop. By observing the cosmic microwave background, we can see the universe as it was 380,000 years after the Big Bang, an ancient light carrying information about the early universe encoded in tiny temperature variations. By studying the abundances of different elements in old stars and gas clouds, we can infer what happened during Big Bang nucleosynthesis in the first minutes. Every observation we make is a window into the past, and by combining observations at different distances and different wavelengths, we can reconstruct the entire history of the cosmos. The methods we use to study the universe are marvels of human ingenuity and technological achievement. We build telescopes that collect and focus light, from radio waves to visible light to X-rays and gamma rays, capturing the faint signals from distant objects and analyzing them to learn about the temperature, composition, velocity, and other properties of their sources. We use spectroscopy, splitting light into its component wavelengths and examining the pattern of bright and dark lines that reveal which elements are present and their physical conditions. We measure the redshift of distant galaxies, the stretching of their light to longer wavelengths caused by the expansion of the universe, and use this to determine their distances and velocities. We use gravitational lensing, where the gravity of massive objects bends light from background sources to map the distribution of dark matter and to magnify distant galaxies that would otherwise be too faint to see. We have sent spacecraft to explore our solar system, visiting all the planets and many moons and asteroids and comets, returning images and data that have transformed our understanding of these worlds. We have landed rovers on Mars that have searched for signs of past water and conditions that might have supported life. We have sent probes to orbit Jupiter and Saturn, revealing the complexity and diversity of their moons, discovering geysers of water ice erupting from Saturn's moon Enceladus, finding a subsurface ocean beneath the icy crust of Jupiter's moon Europa, places where conditions might be suitable for life, even in the cold outer solar system. We have sent the Voyager spacecraft beyond the planets, carrying golden records with sounds and images of Earth as messages to any extraterrestrial intelligence that might someday encounter them. And these spacecraft have now left the heliosphere and entered interstellar space, the first human-made objects to do so. We have built particle accelerators where we collide protons at energies high enough to recreate conditions that existed in the early universe, studying the fundamental particles and forces, discovering the Higgs boson, which gives other particles their mass, testing our theories of particle physics, and exploring the nature of matter and energy at the most fundamental level. We have detected gravitational waves, ripples in the fabric of space-time itself, predicted by Einstein's general relativity, produced by the most violent events in the universe, such as the collision and merger of black holes or neutron stars, opening an entirely new way of observing the cosmos and allowing us to test general relativity in the extreme conditions where gravity is strongest. All of these observations and experiments, combined with theoretical calculations and computer simulations, have given us a remarkably detailed and coherent picture of the universe and its history. The Big Bang Theory is not just speculation, but a scientific theory supported by multiple independent lines of evidence, from the expansion of the universe to the cosmic microwave background, to the abundances of light elements, to the age of the oldest stars, to the distribution of galaxies on large scales. While many questions remain unanswered, while mysteries like dark matter and dark energy and the precise mechanism of inflation still challenge us, the overall framework is well established and continues to be refined and extended as new observations are made and new theoretical insights are developed. One of the most profound questions that emerges from our understanding of the universe is whether life exists elsewhere, whether we are alone in this vast cosmos, or whether life has emerged on other worlds, orbiting other stars in other galaxies. The same processes that led to life on Earth, the formation of planets in habitable zones around stable stars, the delivery of water and organic compounds, the chemistry of carbon-based molecules, should presumably occur throughout the universe, wherever conditions are suitable. And given the hundreds of billions of stars in our galaxy alone, and the trillions of galaxies in the observable universe, it seems almost certain that Earth-like planets must exist in vast numbers. And if the emergence of life is not extraordinarily improbable, then life should be common in the universe. We have begun to search for evidence of extraterrestrial life in various ways. We search for signals from technological civilizations using radio telescopes, listening for artificial transmissions that would indicate the presence of intelligent beings. Though so far we have not detected any convincing signals despite decades of searching. We study Mars and the icy moons of the outer solar system, looking for signs of past or present microbial life, examining rocks and soil samples, measuring the composition of plumes of water vapor, searching for organic molecules and biosignatures. We are developing techniques to analyze the atmospheres of planets orbiting other stars, exoplanets, looking for combinations of gases like oxygen and methane that would be difficult to explain without biology. Though current technology limits us to studying mostly large planets close to their stars, and it will take next-generation space telescopes to study Earth-sized planets in detail. The discovery of exoplanets, planets orbiting stars other than the Sun, has been one of the great achievements of astronomy in recent decades. The first confirmed detections came in the 1990s, and since then, thousands of exoplanets have been discovered using various techniques, primarily the transit method, where we observe the slight dimming of a star's light when a planet passes in front of it, and the radial velocity method, where we measure the wobble in a star's motion caused by the gravitational pull of orbiting planets. These discoveries have revealed that planetary systems are common, that planets come in a wide variety of sizes and compositions, including types not found in our solar system, like hot Jupiters, gas giants orbiting very close to their stars, and super-Earths, rocky planets larger than Earth but smaller than Neptune. Many stars have multiple planets, and some planets orbit in the habitable zone, where temperatures could allow liquid water to exist on their surfaces. The diversity of exoplanetary systems has forced us to revise our understanding of planet formation, for we have found systems very different from our solar system, with giant planets close to their stars, suggesting that planets can migrate inward after forming, with planets on highly eccentric orbits, indicating that gravitational interactions can dramatically alter orbital configurations, with planets orbiting binary star systems and even free-floating planets ejected from their stellar systems entirely. This diversity suggests that the specific arrangement of our solar system, with small rocky planets close to the Sun and giant planets farther out, with nearly circular orbits, all in roughly the same plane, may not be typical. And understanding why different systems have different architectures remains an active area of research. The search for life beyond Earth is not just about finding microbes on Mars or detecting signals from alien civilizations, profound as those discoveries would be, but also about understanding our own place in the universe, about learning whether the origin of life on Earth was a unique accident or an inevitable consequence of cosmic evolution, about discovering whether consciousness and intelligence are rare or common, about finding out if we have cosmic companions, or if we are, for now at least, alone in a vast and ancient universe. The answer to this question has profound implications for how we view ourselves and our significance, for our understanding of biology and the nature of life itself, for our future as a species and our potential to spread beyond Earth and become a spacefaring civilization. As we contemplate the future of humanity, we cannot help but consider our place in this cosmic context. We are creatures who evolved on a single planet, orbiting a single star in a single galaxy among trillions. Yet we have developed the capability to understand the entire universe, to trace its history back to the Big Bang, to predict its future over timescales that dwarf the entire history of life on Earth. We have landed on the Moon and sent robots to Mars, and probes to the outer solar system and beyond. We have built telescopes that can see galaxies billions of light years away, and particle accelerators that can probe the structure of matter at scales smaller than a proton. We have decoded the human genome and begun to understand the molecular basis of life. We have created art and music and literature, built civilizations, developed language and mathematics and science, and in doing so have become, as far as we know, the universe's way of understanding itself. Yet we also face challenges that threaten our long-term survival and flourishing. Climate change, driven by our burning of fossil fuels, is altering Earth's environment in ways that could make it less hospitable for us and for many other species. Nuclear weapons give us the power to devastate our civilization in a matter of hours. Resource depletion, pollution, loss of biodiversity, and other environmental problems threaten the stability of the ecosystems on which we depend. Social and political conflicts, inequality, and other challenges test our ability to cooperate and work together to solve problems. Whether we successfully navigate these challenges and build a sustainable future, or succumb to them and potentially cause our own extinction, remains to be determined by our choices and actions in the coming decades and centuries. If we do survive and thrive, if we continue to develop our technology and expand our presence beyond Earth, we might imagine a future where humanity, or its descendants, spread throughout the solar system, establishing permanent settlements on the Moon and Mars and the moons of Jupiter and Saturn, mining asteroids for resources, building rotating space habitats where people can live in comfort with artificial gravity, developing closed-loop life support systems that recycle everything and require minimal resupply from Earth. We might eventually develop the technology to send robotic probes or even crewed missions to other star systems. Though the distances are daunting, with even the nearest star beyond the Sun, Proxima Centauri, being 4.2 light-years away, requiring travel times of decades or centuries with any propulsion system we can currently envision, and reaching more distant stars requiring even longer journeys. Some visions of the far future imagine humanity spreading across the galaxy over millions of years, terraforming planets to make them suitable for life, building megastructures like Dyson spheres that capture most or all of a star's energy output, even eventually colonizing other galaxies if we can find ways to traverse the vast intergalactic distances. Other scenarios imagine us developing artificial intelligence that surpasses human intelligence and takes over the process of exploration and development, or merging with our technology to become post-biological beings, or discovering new physics that allows faster-than-light travel or communication. These speculations are, of course, highly uncertain, based more on imagination than on concrete knowledge. But they remind us that the future is open, that the story of the universe is not finished, that there may be many chapters yet to be written. But even if humanity survives for millions or billions of years, even if we spread across the galaxy or beyond, we remain subject to the same physical laws that govern the rest of the universe. And the ultimate fate of the universe will eventually affect us as well. When the Sun exhausts its hydrogen fuel in about 5 billion years, it will swell into a red giant star, expanding to perhaps the orbit of Earth or beyond, engulfing the inner planets, or at least rendering them uninhabitable, before eventually shedding its outer layers and leaving behind a white dwarf that will slowly cool over trillions of years. Long before this happens, in perhaps 1 billion years or so, the Sun's gradually increasing luminosity will heat Earth enough that the oceans will evaporate and life as we know it will become impossible, forcing any surviving humans or their descendants to migrate to other worlds or find technological solutions to maintain habitability. The Milky Way and Andromeda galaxies are currently approaching each other at about 100 kilometers per second, and in about 4 billion years they will begin to merge, a process that will take several billion years to complete as the two galaxies pass through each other, interact gravitationally, and eventually settle into a single, large elliptical galaxy. Despite the enormous numbers of stars involved, the distances between stars are so vast that direct collisions between stars will be rare, and most stars will simply be redistributed into new orbits in the merged galaxy. However, the gravitational interactions during the merger will likely trigger bursts of star formation as gas clouds are compressed, and some stars may be flung out of the merged galaxy entirely, ejected by close encounters with other stars or by the changing gravitational potential, becoming intergalactic wanderers traveling alone through empty space. On even longer timescales, the accelerating expansion of the universe, driven by dark energy, would eventually carry most galaxies beyond our cosmic horizon, making them permanently inaccessible to us, or to any beings that might exist in the far future Milkomeda galaxy. The local group will remain bound together by gravity, but everything outside it will gradually recede and disappear. And observers in that future time will see a much emptier universe than we do, with only the stars of their own merged galaxy visible against a dark sky, the rest of the universe having been carried away by cosmic expansion. They will face the challenge of inferring the existence and history of the broader universe from whatever evidence remains in their local region, from the composition and ages of stars, from the cosmic microwave background, if they can still detect it, from theoretical reasoning, and perhaps from historical records, if knowledge is preserved over these vast times. As we contemplate these vast scales of space and time, as we trace the history of the universe from the Big Bang through billions of years of cosmic evolution to the present, and project forward into a future measured in trillions of years and beyond, we might feel a sense of insignificance, a recognition of how small and brief we are compared to the immensity of the cosmos. We live for decades on a planet that is 4.5 billion years old, in a universe that is 13.8 billion years old, and will likely continue for trillions of years or more. We occupy a tiny speck of rock orbiting an ordinary star in an ordinary galaxy, one of trillions of galaxies spread across a space so vast that light takes billions of years to cross it. In the grand scheme of cosmic history, human civilization has existed for only the briefest moment, and even if we survive for millions of years into the future, we will still be a fleeting episode in the story of the universe. Yet we might also feel a sense of wonder and privilege, a recognition that despite our smallness, we are part of this magnificent cosmos, made of atoms that were forged in stars, governed by the same physical laws that operate throughout the universe, connected through an unbroken chain of causation, stretching back to the Big Bang itself. We are complex structures that have emerged from simpler components through the processes of cosmic and biological evolution, organized arrangements of matter that have developed the remarkable properties of life and consciousness and intelligence. We can observe the universe and seek to understand it. We can appreciate its beauty and contemplate its mysteries. We can wonder about our place in it and imagine its future. In a universe that is mostly empty space and dark matter and dark energy, where most matter is cold and inanimate, where consciousness may be rare or even unique to Earth, the fact that we exist at all, that we can think and feel and question, seems both improbable and precious. The journey we have taken together through cosmic history, from the incomprehensible conditions at the moment of the Big Bang, through the formation of particles and atoms, through the ignition of the first stars and the assembly of galaxies, through the formation of our solar system and the emergence of life on Earth, to the present day and beyond into the far future, is a story grounded in observation and theory, in mathematics and physics, in the patient work of countless scientists over many generations who have pieced together this understanding from fragments of evidence, from the light of distant galaxies, from the cosmic microwave background, from the patterns of elements in stars, from the behavior of particles in accelerators, from gravitational waves, from the orbits of planets and the ages of rocks, and 1,000 other clues. It is also a story that speaks to something deep in human nature, our desire to understand where we came from and where we are going, our need to find meaning and context for our existence, our capacity for awe and wonder when confronted with the sublime and the infinite. Throughout human history, every culture has had creation stories, myths, and legends that explain the origin of the world and the heavens, often involving gods and supernatural events, expressing in narrative form the questions that all people ask about existence. The scientific story of the Big Bang and cosmic evolution is our modern creation myth, different from ancient myths in that it is based on evidence and can be tested and revised as we learn more, but similar in that it addresses the same fundamental questions and provides a framework for understanding our place in reality. As we near the end of our journey through cosmic time, as the narrative of the universe's history, from past to future, draws toward completion, let us pause for a moment to reflect on the profound interconnectedness of everything we have described. The expansion of the universe, begun at the Big Bang and continuing today, set the stage for everything that followed, determining the timeline of cosmic evolution, the rate at which the universe cooled, the density at which structures could form, the physics of the early universe, the behavior of particles and forces in extreme conditions, determined which elements were created in Big Bang nucleosynthesis and in what proportions. And these proportions, in turn, influence the formation and evolution of stars. The first stars, burning bright and dying young, enriched the pristine hydrogen and helium with heavier elements, making possible the formation of rocky planets and the chemistry of life. Gravity, acting over billions of years, pulled matter into galaxies and galaxy clusters, creating the cosmic web we observe today. Dark matter, though invisible, provided the gravitational scaffolding along which ordinary matter could accumulate and form visible structures. Dark energy, driving the accelerated expansion, determines the ultimate fate of the universe and the maximum extent to which structure can grow. Every atom in your body, every carbon atom in your DNA, every calcium atom in your bones, every iron atom in your blood, was created either in the Big Bang, in the case of hydrogen, or in the core of a star, or in a supernova explosion, in the case of heavier elements, and has been recycled through multiple generations of stars and planets before becoming part of you. You are literally made of stardust, a collection of atoms that are billions of years old, that have been part of interstellar gas clouds and ancient stars and the disk from which the solar system formed and the body of the early Earth, and countless organisms over billions of years of evolution. The oxygen you breathe was produced by stars more massive than the Sun that exploded as supernovae billions of years ago, scattering their ashes into space. The water you drink contains hydrogen nuclei that are almost as old as the universe itself, forged in the first minutes after the Big Bang. Combined with oxygen, much later in stars, formed into water molecules, perhaps in the early solar system, or on Earth itself, or delivered by comets from the outer reaches. The light that enters your eyes, whether from the sun or from a distant star, has traveled across space, carrying energy and information, photons that were emitted from the surface of a star, and have journeyed through the vacuum, perhaps for years or centuries or millions of years, until they happen to encounter your eye and be absorbed by molecules in your retina, triggering a cascade of chemical reactions that eventually results in your perception of light and color and form. When you look at the night sky, you are directly observing the universe, seeing ancient light from distant sources, witnessing cosmic history unfolding before you, connected through this light to events and places far beyond your everyday experience. The universe is vast and ancient and mostly empty, cold and dark on average, governed by impersonal physical laws that operate without purpose or intent, indifferent to our existence. Yet within this immense cosmos, in at least one small corner that we know of, complexity has emerged, life has arisen, consciousness has developed, beings have appeared who can observe and understand and appreciate the universe that created them. Whether this has happened in other places, whether we have cosmic companions or are alone, remains unknown, but either answer would be profound. If we are alone, then consciousness may be vanishingly rare in the universe, and our existence and survival become even more precious as possibly the only way the universe can know itself. If life and consciousness are common, then we are part of a greater community, and somewhere among the stars, there may be other beings looking up at their own night skies and asking the same questions we ask, wondering about their origins and their place in the cosmos. Perhaps also discovering the story of the Big Bang and cosmic evolution, arriving at the same truths about the universe through their own methods of observation and reason. As our long journey through cosmic time and space approaches its conclusion, as we have traveled from the initial singularity through 13.8 billion years of history to the present, and gazed into a future extending trillions upon trillions of years ahead, we return to where we began, to this moment, to this present, to the universe as it is now, with you, here, listening to these words, breathing steadily, feeling perhaps the weight of your body against whatever surface supports you, the gentle rhythm of your heartbeat, the soft flow of your breath, in and out, connecting you to the atmosphere of Earth, which is itself a product of billions of years of geological and biological evolution, maintained by living processes, a thin shell of gas surrounding a rocky planet orbiting a middle-aged star in a spiral galaxy. All of this part of a universe that began in a singularity and has been evolving ever since according to the laws of physics. You are part of this cosmic story, not separate from it, but woven into its fabric, a pattern of matter and energy that has organized itself into the form of a living, conscious being, experiencing the universe from within, able to contemplate your own existence and the nature of reality itself. Your awareness, your consciousness, is perhaps the most mysterious and wonderful phenomenon in all of nature. Something that emerges from the physical interactions of neurons in your brain, yet cannot be fully reduced to or explained by those physical processes. A subjective experience of being that accompanies the objective functioning of biological systems, creating an inner universe of thoughts and feelings and perceptions and dreams that is private and immediate and known only to you. As you rest now, listening to the story of the cosmos, you might feel yourself settling more deeply into relaxation, your breathing becoming slower and more regular, your body growing heavier and more comfortable, your mind beginning to drift, the concerns and thoughts of the day gradually fading into the background as the gentle rhythm of cosmic time flows through the narrative, carrying you along like a leaf on a vast and ancient river, not fighting or resisting, but simply floating, allowing yourself to be held and supported by forces larger than yourself, by the same forces that have shaped the universe and created everything in it, including you. The universe, for all its vastness and complexity, for all the violence of supernovae and the intense gravity of black holes, for all the tremendous energies and extreme conditions that exist in various places and times, is also a place of extraordinary beauty and order, where simple laws give rise to rich structures, where atoms combine into molecules, and molecules into cells, and cells into organisms, where stars shine steady for billions of years, providing the stable conditions needed for planets and life, where galaxies dance in great slow spirals, where light travels across the void, carrying information and energy, connecting distant parts of the cosmos, creating a unity underlying the diversity. And now, having traversed this immense landscape of space and time, having witnessed the birth of the universe in the Big Bang and followed its evolution through all the eons that followed, having seen how structure emerged from uniformity, how complexity arose from simplicity, how consciousness appeared from unconsciousness, we can rest in the knowledge that we are part of this grand story, temporary manifestations of the universe's ongoing evolution, patterns that will eventually dissolve back into the cosmic flow. Our atoms returning to the cycle of creation and destruction that has been operating since the beginning, perhaps to be incorporated into future stars or planets, or even future beings, who will live their own lives and ask their own questions and marvel at the same stars we see today, continuing the story into a future we can barely imagine. Let your breathing slow now, deep and regular, like the slow expansion of the universe itself, like the patient flow of cosmic time, each breath taking you deeper into rest, each exhalation releasing tension and thought, leaving only a peaceful awareness, a quiet presence, the gentle sensation of existing in this moment, suspended between the ancient past and the far future, part of an eternal present that is always here, always now, the only moment that truly exists, the point where the past is remembered and the future is imagined, but neither is real in the way that this present moment is real. The stars continue to shine in the darkness of space, photons streaming outward from their surfaces, carrying energy across the light years, some of them destined to fall on planets where eyes might receive them, others to wander through empty space for eternity. Galaxies continue their slow rotation, stars orbiting around galactic centers in paths that will carry them around hundreds of times before the stars themselves die. The cosmic web maintains its structure, filaments of galaxies spanning the observable universe, surrounding vast voids where few galaxies exist. A pattern that is slowly evolving as structure continues to grow on the largest scales, as galaxy clusters merge and galaxies within them interact and exchange matter. The universe expands, space itself growing, carrying galaxies apart, the distance between them increasing with each passing moment, a process that has been occurring for 13.8 billion years and will continue for trillions more, perhaps forever, driven by dark energy whose nature we do not fully understand, but whose effects we can measure and predict. This expansion, this increase in scale, this growing of space, means that the universe is becoming less dense, more diffuse, cooler on average, gradually running down from the intense heat and density of the Big Bang toward the cold darkness of the far future. Not catastrophically, but slowly, gently, inevitably, following the laws of thermodynamics that govern all physical processes. In this expanding universe, on this small planet, in this present moment, you are resting, your body relaxed, your mind quiet, your breathing slow and steady, perhaps beginning to drift towards sleep, that mysterious state where consciousness fades and dreams arise, where the brain continues its work of processing and consolidating memories, where the body repairs and renews itself, where you are temporarily released from the need to act or think or plan, simply being, simply existing, held safely by the same forces that hold planets in their orbits and bind atoms together and guide photons across space at the speed of light. Sleep is itself a kind of journey, a nightly voyage into an inner world of dreams and unconsciousness, a letting go of waking awareness, a surrender to natural biological rhythms that have evolved over millions of years, that are shared by countless species, that connect you to all life on Earth, and perhaps, if life exists elsewhere, to living beings throughout the universe who also sleep and dream and wake, experiencing their own versions of consciousness and existence. As you drift towards sleep now, you are following a path as natural and ancient as the stars themselves, as fundamental as the expansion of the universe, as simple as the flow of time from past through present into future. Let the story of the universe hold you gently in its vast embrace. Let the knowledge that you are made of star stuff comfort you. Let the understanding that you are part of an ancient and ongoing cosmic process give you peace. You are exactly where you need to be, exactly when you need to be here. A conscious observer in a universe that has been evolving for nearly 14 billion years. A being capable of knowing and understanding and appreciating the cosmos. Connected to everything through the web of causation that links all events and all things, from the Big Bang to this present moment, to whatever future lies ahead. The cosmic microwave background continues to bathe the universe in its faint glow, that ancient light from 380,000 years after the Big Bang, now cooled to a temperature of about 2.7 degrees above absolute zero, filling all of space uniformly in every direction. A constant reminder of the universe's hot, dense past, carrying, encoded in its tiny temperature fluctuations, a wealth of information about the early universe that astronomers have painstakingly extracted and analyzed. This radiation, invisible to our eyes, but detectable with sensitive instruments, is perhaps the most direct evidence we have of the Big Bang itself, a fossil from the early universe that has survived to the present day, traveling through space for over 13 billion years, maintaining its characteristic thermal spectrum even as it has been stretched to longer and longer wavelengths by the expansion of space. When scientists first understood the implications of the cosmic microwave background, when they realized that its existence and properties matched precisely what the Big Bang theory predicted, it provided compelling confirmation of this theory and transformed cosmology from a field based largely on philosophical speculation into a rigorous science grounded in observation. The uniformity of this radiation, the fact that it has almost exactly the same temperature in all directions, with variations of only about 1 part in 100,000, told cosmologists that the early universe was remarkably smooth and homogeneous, presenting a puzzle because the universe today is clearly not homogeneous, with matter clustered into galaxies and galaxy clusters separated by vast voids. The solution to this puzzle came from the theory of cosmic inflation, which explained both the uniformity by proposing that all the observable universe came from a tiny region that was smooth and then expanded exponentially, and the origin of structure by proposing that quantum fluctuations in this tiny region were amplified by inflation to create the density variations that would eventually grow into galaxies. The cosmic microwave background has been studied in increasingly fine detail by a series of experiments and satellite missions, from the initial discovery by Penzias and Wilson in 1964 through the COBE satellite in 1989 that first detected the tiny temperature variations across the sky, to the WMAP satellite in 2001 and the Planck satellite in 2009, each providing more precise measurements and revealing more information about the universe's composition, geometry, and evolution. These measurements have determined the age of the universe to within about 1%, measured the proportions of ordinary matter, dark matter, and dark energy to within a few percent, constrained the properties of the primordial density fluctuations, tested the predictions of inflation, and provided evidence for or against various theoretical ideas about the universe's origin and evolution. Few discoveries in the history of science have proven as fruitful as the cosmic microwave background, and it continues to be studied today with ground-based experiments looking for even fainter signals that might reveal new aspects of the early universe. Dark matter, that mysterious substance that makes up most of the matter in the universe, remains one of the great unsolved problems in physics. We know it exists because we can observe its gravitational effects, the way it causes galaxies to rotate faster than they should, based on their visible matter alone, the way it holds galaxy clusters together with more gravity than their visible matter could provide, the way it bends light from background galaxies through gravitational lensing, creating arcs and multiple images that reveal the distribution of total mass in clusters. We can map the distribution of dark matter across the universe by observing these gravitational effects, and we find that it forms a cosmic web of filaments and nodes, a scaffolding along which and at which galaxies form. Yet, despite decades of searching, we have not directly detected dark matter particles or determined what they are made of, though there are many theoretical candidates, including weakly interacting massive particles called WIMPs, axions, sterile neutrinos, and more exotic possibilities. The search for dark matter involves multiple approaches, from building ultra-sensitive detectors deep underground to shield them from cosmic rays, hoping to catch the rare interaction of a dark matter particle with ordinary matter, to looking for the products of dark matter particles annihilating with each other in space and producing detectable radiation, to creating dark matter particles in particle accelerators by colliding ordinary particles at high energies, and looking for missing energy that would indicate dark matter was produced and escaped without being detected. So far, despite these extensive efforts, dark matter particles have eluded detection, suggesting either that our experimental sensitivity is not yet good enough, or that dark matter interacts even more weakly with ordinary matter than we thought, or that our understanding of what dark matter is might need to be revised. Some researchers have even proposed that dark matter might not be particles at all, but rather a modification of the law of gravity on large scales, though such theories have difficulty explaining all the observations as successfully as particle dark matter does. Dark energy, the mysterious force or energy that is causing the universe's expansion to accelerate, is even more puzzling than dark matter. discovered in 1998 through observations of distant Type Ia supernovae, which appeared fainter than expected, indicating they were farther away than they should be in a universe whose expansion was slowing down. Dark energy seems to be a property of space itself, a sort of vacuum energy or cosmological constant that creates a repulsive gravitational effect, pushing space apart rather than pulling it together. The density of dark energy appears to be constant as the universe expands, meaning that as space grows, the total amount of dark energy increases proportionally, unlike matter whose density decreases as the universe expands, and this leads to dark energy becoming increasingly dominant over time, as it is today, making up about 68% of the total energy content of the universe. The nature of dark energy is one of the deepest mysteries in physics, for while we can measure its effects and include it in our cosmological models, we do not understand what it is or why it has the particular density that it does. Theoretical calculations suggest that the vacuum energy of empty space, arising from quantum fluctuations, should be enormously larger than the observed dark energy density, larger by a factor of 10 to the 120, an absurdly wrong prediction that represents one of the worst mismatches between theory and observation in all of science. This suggests that either our understanding of vacuum energy is fundamentally wrong, or there is some mechanism that cancels out most of the vacuum energy, leaving only the small observed amount. Or dark energy is not vacuum energy at all, but something else entirely. Perhaps a slowly evolving field called quintessence, or a modification of general relativity on cosmological scales, or something even more exotic that we have not yet imagined. Whatever dark energy is, its effects are profound and will determine the ultimate fate of the universe. If dark energy continues to behave as it does today, maintaining a constant density as space expands, then the universe will continue to expand exponentially, doubling in size at regular intervals, eventually carrying all galaxies outside our local group beyond our cosmic horizon, leaving us in an increasingly isolated island universe surrounded by empty space. If dark energy were to increase in density over time, as some theories predict, it could eventually become so dominant that it would overcome all other forces, ripping apart galaxy clusters, then galaxies, then stars, then planets, then atoms themselves, in what has been called the Big Rip, tearing apart all structure in the universe in a final catastrophic event. Conversely, if dark energy were to decrease or even reverse sign, the expansion could slow and eventually halt, leading to a big crunch where the universe collapses back in on itself, though current observations suggest this scenario is unlikely. The quantum nature of reality, revealed through experiments in the early 20th century and formalized in the theory of quantum mechanics, adds another layer of mystery and wonder to our understanding of the universe. At the smallest scales, reality is fundamentally probabilistic rather than deterministic, with particles not having definite properties until they are measured, existing instead in superpositions of multiple states simultaneously. The famous uncertainty principle tells us that certain pairs of properties, like position and momentum, cannot both be known precisely at the same time, setting fundamental limits on what can be measured and predicted. Particles can tunnel through barriers that classical physics says they should not be able to cross, can be entangled with each other such that measuring one instantly affects the other, even across vast distances, can be created and destroyed in pairs from the vacuum in fleeting quantum fluctuations that violate energy conservation for brief instants allowed by the uncertainty principle. These quantum effects, though strange and counterintuitive, have been verified in countless experiments and are essential to understanding the behavior of atoms and molecules, the structure of matter, the operation of modern technology, from computer chips to lasers to MRI machines. Quantum mechanics is the foundation of chemistry and materials science, explaining the periodic table and the bonding of atoms into molecules, the properties of metals and semiconductors and insulators, the behavior of light and its interaction with matter. Yet, despite its tremendous success in explaining and predicting the behavior of microscopic systems, quantum mechanics remains deeply puzzling at a philosophical level, raising questions about the nature of reality, the role of observation and measurement, the meaning of probability, the relationship between quantum and classical descriptions of the world. The attempt to unify quantum mechanics with general relativity, to create a theory of quantum gravity that would describe the behavior of space-time at the smallest scales and the highest energies, has been one of the great challenges in theoretical physics for nearly a century. General relativity describes gravity as the curvature of space-time caused by mass and energy, working beautifully at large scales, but breaking down at the singularities inside black holes and at the moment of the Big Bang, where densities and curvatures become infinite. Quantum mechanics describes the other three forces of nature, the electromagnetic, weak, and strong nuclear forces, in terms of quantum fields and particle exchanges, but attempts to apply the same approach to gravity have led to mathematical difficulties and infinities that cannot be removed by standard techniques. Various approaches to quantum gravity have been proposed, including string theory, which suggests that fundamental particles are actually tiny, vibrating strings in 10-dimensional space-time, and loop quantum gravity, which attempts to quantize space-time itself. But so far, none has been completely successful or universally accepted. String theory, despite remaining unproven and controversial, has led to fascinating ideas about the nature of reality, suggesting that there might be extra dimensions of space beyond the three we perceive, curled up so small that we cannot detect them directly, and that our universe might be just one of many in a vast multiverse of universes with different physical properties. The landscape of possible universes in string theory is enormous, perhaps 10 to the 500 different solutions or more each, representing a universe with different values for physical constants, different particle masses, different forces, raising the question of why our universe has the particular properties it does. One possible answer is the anthropic principle, the idea that we observe the universe we do because we could not exist in most other possible universes, that the physical constants must be in a narrow range that allows atoms and stars and planets and life to exist, and we necessarily find ourselves in such a universe because we could not be here to observe it otherwise. These questions about the ultimate nature of reality, about why the universe exists at all, and why it has the particular laws and properties it does, push us to the boundaries of what science can address. Science excels at answering how questions, at describing the mechanisms and processes by which things happen, at making predictions and testing them against observations. But it is less well suited to answering why questions about ultimate purposes or reasons. Why does the universe exist rather than nothing? Why do the laws of physics have the form they do? Why are the physical constants fine-tuned to allow the existence of complex structures and life? These questions may ultimately be beyond the reach of science, may require philosophical or metaphysical reasoning, or may simply have no answer in the sense that we would like, no deeper explanation beyond the brute fact that this is how things are. Yet even if some questions remain forever beyond our reach, the scientific enterprise of observing, experimenting, theorizing, and testing has proven extraordinarily successful at expanding our knowledge and understanding of the natural world. From the ancient Greeks, who proposed that matter was made of atoms and who developed the first mathematical descriptions of nature, through the scientific revolution of the 16th and 17th centuries, when Copernicus and Galileo and Kepler and Newton established the heliocentric model and the laws of motion and gravitation, through the 19th century discoveries of electromagnetism and thermodynamics and evolution, through the 20th century revolutions of relativity and quantum mechanics, and the discovery of the expanding universe, to the present day when we map the cosmos with unprecedented precision and probe matter at the smallest scales and send robots to other worlds. Science has revealed a universe far stranger and more wonderful than anyone could have imagined. A cosmos of immense age and size, governed by elegant mathematical laws, filled with phenomena ranging from the familiar to the bizarre, from the mundane to the sublime. The process of science, at its best, is a collective human endeavor that transcends individual limitations, where many minds working together, building on each other's work, checking and correcting each other's mistakes, gradually accumulate knowledge that becomes more and more refined and accurate. Theories are proposed and tested against observation, and those that survive testing are tentatively accepted, while those that fail are modified or discarded, in a process that is self-correcting and progressive, not because scientists are more rational or objective than other people, but because the method itself, when properly applied, tends toward truth, even when individual scientists are biased or mistaken. The history of science is full of wrong ideas that were believed for centuries before being overturned, of controversies and disputes, of discoveries that were resisted or rejected before being accepted. But the overall trajectory has been toward greater understanding, toward more accurate and comprehensive theories, toward a clearer picture of reality. In recent decades, our observational capabilities have increased dramatically, with space telescopes that observe in wavelengths from radio to gamma rays, with gravitational wave detectors that sense ripples in space-time itself, with neutrino observatories deep underground or in Antarctic ice, with particle accelerators that recreate conditions from the early universe, with supercomputers that simulate cosmic evolution or stellar interiors or galactic collisions, with worldwide networks of astronomers and physicists sharing data and collaborating on projects too large for any single institution or nation. These tools have revealed a universe of astonishing diversity and complexity, from the delicate filaments of the cosmic web stretching across billions of light years, to the violent environments around supermassive black holes where matter spirals inward at nearly the speed of light, to the exotic physics of neutron stars where matter is compressed to nuclear densities, to the gradual evolution of galaxies over billions of years, to the formation of planets around other stars and the possibility of life beyond Earth. Each new discovery raises new questions, opens new avenues of inquiry, reveals new mysteries to be explored. When we discovered that the universe is expanding, we were led to ask where the expansion came from and what came before, leading to the Big Bang theory. When we discovered the cosmic microwave background, we were led to ask about the physics of the early universe, leading to theories of Big Bang nucleosynthesis and recombination. When we discovered dark matter and dark energy, we were led to ask about the nature of these mysterious components that dominate the universe, yet remain invisible and poorly understood. When we discovered exoplanets, we were led to ask about their diversity and how they form and whether they might harbor life. Each answer generates new questions in an endless process of inquiry that shows no signs of reaching completion, suggesting that our understanding of the universe will continue to deepen and expand for as long as we continue to observe and question and explore. The development of technology has been intimately linked with scientific discovery, with new instruments enabling new observations that lead to new theories, and new theories suggesting new experiments that drive the development of new technologies. The telescope, invented in the early 17th century and quickly turned skyward by Galileo, revolutionized astronomy by revealing the moons of Jupiter, the phases of Venus, the countless stars of the Milky Way, providing crucial evidence for the Copernican heliocentric model. The spectroscope, developed in the 19th century, allowed astronomers to analyze the light from stars and determine their composition and temperature and motion. transforming astronomy from a science of positions and motions into a science that could study the physical properties of distant objects. Photography, first applied to astronomy in the mid-19th century, allowed the accumulation of faint light over long exposures, revealing objects far too dim to be seen by eye, and creating permanent records that could be studied and compared. In the 20th century, the development of radio astronomy opened an entirely new window on the universe, revealing phenomena like pulsars and quasars that emit primarily in radio wavelengths, mapping the structure of the Milky Way through observations of radio emission from hydrogen gas, detecting the cosmic microwave background. Space-based observatories, free from the blurring and absorption of Earth's atmosphere, have observed in infrared, ultraviolet, X-ray, and gamma-ray wavelengths that are blocked by the atmosphere, revealing hot gas in galaxy clusters, the violent environments around black holes, the formation of stars in dusty clouds, the remnants of supernovae. Gravitational wave detectors, first achieving detection in 2015 after decades of development, have opened an entirely new way of observing the universe, sensing the ripples in space-time produced by colliding black holes and neutron stars, providing information that is completely independent of electromagnetic radiation and complementary to it. Computer simulations have become an essential tool in modern cosmology and astrophysics, allowing researchers to model processes that cannot be easily studied in the laboratory or through observation alone. Simulations of galaxy formation start with the initial conditions from the cosmic microwave background and follow the evolution of dark matter and gas under gravity and hydrodynamics over billions of years, producing synthetic universes that can be compared with observations to test theories of structure formation. Simulations of stellar evolution follow individual stars through their lifetimes, calculating how they burn fuel, how they change in structure and composition, how they die, and what remnants they leave behind. Simulations of the early universe explore the physics of inflation and Big Bang nucleosynthesis, and the formation of the first stars. These simulations require enormous computational resources, running on supercomputers with thousands or millions of processors working in parallel, and they have become increasingly sophisticated and realistic, though they still involve approximations and simplifications that limit their accuracy. The mathematical language in which the laws of physics are expressed has proven remarkably effective at describing nature, leading to what physicist Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. The surprising fact that abstract mathematical structures invented by pure mathematicians often turn out to describe physical reality with great precision. General relativity is formulated in the language of differential geometry, a branch of mathematics that studies curved spaces, and this mathematical framework allows predictions of phenomena like gravitational waves and black holes that were completely unexpected when the theory was first developed. Quantum mechanics is formulated using linear algebra and complex numbers and probability theory, mathematical tools that allow precise calculations of atomic properties and molecular behavior. The Standard Model of Particle Physics, which describes all known particles and 3 of the 4 fundamental forces, is written in the language of quantum field theory and group theory, abstract mathematical structures that somehow capture the essential physics of the subatomic world. This deep connection between mathematics and physics remains mysterious, for while we can observe that it works, we do not fully understand why. Is mathematics something we invent, a human creation that we impose on nature to make sense of it? And the effectiveness of mathematics is just a reflection of the fact that we have developed mathematical tools specifically to describe the patterns we observe? Or is mathematics something we discover, an existing structure that is somehow built into the fabric of reality itself, independent of human minds, and mathematical laws are the true fundamental reality underlying physical phenomena? This question touches on deep issues in the philosophy of mathematics and science, and there is no consensus answer, though most working physicists behave as if mathematical laws are genuine discoveries about objective reality, rather than convenient fictions we have invented. As we continue this gentle journey through the story of the cosmos, through the vast scales of time and space that characterize our universe, through the intricate dance of matter and energy that has produced all the complexity and beauty we observe, we might feel a sense of connection to this grand narrative, a recognition that our individual stories are part of a much larger story, that our brief lives are embedded in a cosmos that has existed for nearly 14 billion years and will continue for trillions more. The atoms that make up your body have been on their own cosmic journey, forged in stars that lived and died billions of years ago, drifting through space as part of interstellar gas clouds, eventually collected into the disk from which the sun and planets formed, incorporated into the rock and water and atmosphere of the early Earth, cycle through countless organisms over billions of years of evolution, and now temporarily organized into the specific pattern that is you, maintaining your structure and function through the constant flow of energy and matter that characterizes all living things. You are not a static object, but a dynamic process, a pattern that persists even as the specific atoms that instantiate it are constantly being replaced through metabolism, through breathing and eating and drinking and eliminating waste. The atoms in your body today are not the same atoms that were in your body a year ago, yet you persist as a coherent entity, an organized structure maintained far from equilibrium by the flow of energy from the sun through the food chain to your cells, where it powers the molecular machines that keep you alive. This is the nature of life, not a thing, but a process, not being, but becoming, a temporary eddy in the river of cosmic evolution, stable for a time, but ultimately transient, destined to dissolve back into the flow when death comes and the processes that maintain your organization cease and your atoms return to the environment to be incorporated into other structures, other beings, continuing the eternal recycling of matter that has been operating since the first stars began returning their material to space. The impermanence of all things, the constant change and flux that characterizes reality at every scale, from the quantum fluctuations of particles to the evolution of the universe as a whole, might seem cause for sadness or anxiety, but it can also be a source of peace and acceptance. Everything that exists is temporary. Everything that arises will eventually pass away, from the briefest subatomic particle to the longest-lived star, from individual organisms to entire species, from planets to galaxies to the universe itself in its current form. This is not a failure or a flaw, but simply the nature of reality, the way things are. And accepting this can free us from the futile struggle to make permanent what is inherently impermanent, can help us appreciate and enjoy what exists now without clinging to it or demanding that it last forever. In many wisdom traditions, this recognition of impermanence is seen as liberating, as helping to reduce suffering that comes from attachment to things that cannot last. Buddhism explicitly teaches that attachment to impermanent things is a root cause of suffering, and that accepting impermanence leads to equanimity and peace. Stoic philosophy counsels acceptance of what is beyond our control, including the eventual loss of everything we have and everyone we love, and recommends focusing on what we can control, our own thoughts and responses and character. Modern existential philosophy grapples with the meaning and value of individual human life in a universe that appears indifferent to our existence, finding meaning not in any cosmic purpose, but in the act of living itself, in choosing how to respond to our situation, in creating our own values and projects and commitments. These philosophical perspectives, while developed independently of modern cosmology, resonate with the scientific understanding of the universe as a place without inherent meaning or purpose, where we exist as temporary patterns of matter and energy, where the cosmos will continue its evolution long after humanity and all its works have vanished. Yet this can be experienced not as nihilism or despair, but as freedom and opportunity. For if there is no predetermined cosmic purpose, then we are free to create our own meanings and purposes, to decide for ourselves what is valuable and what is worth doing, to live authentically according to our own understanding, rather than trying to fulfill some external mandate. The universe may be indifferent to our existence, but we are not indifferent to our own existence or to each other. And the meanings we create, though not cosmic or eternal, are real and significant for us during the time we have. As you rest here, breathing softly, your body relaxed and comfortable, your mind quiet and drifting, perhaps you can sense your place in this vast cosmic story, not as something separate from the universe, but as an integral part of it, a way that the universe experiences itself, a localized perspective from which the cosmos can be observed and understood and appreciated. Your consciousness, whatever it is, and however it arises from the physical processes in your brain, is part of the universe, not separate from it. And in your awareness of the stars and galaxies, in your contemplation of cosmic history, the universe is in some sense becoming conscious of itself. Matter organized in such a way that it can reflect on its own existence and origins. This is perhaps the most profound and beautiful aspect of the entire cosmic story, that through billions of years of evolution, from the simplest structures formed in the early universe to the magnificent complexity of living things and conscious minds, the universe has produced beings who can understand it, who can trace its history from the Big Bang forward, who can appreciate its beauty and wonder at its mysteries. We are the universe knowing itself, a remarkable achievement of cosmic evolution. And while our individual existence is brief and our species may be transient on cosmic timescales, the fact that we exist at all, that consciousness has emerged from unconscious processes, that meaning and value have arisen in a universe that began with no meaning or value, is extraordinary and precious. The night sky, when viewed from a location free of light pollution, displays thousands of stars visible to the naked eye, each one a sun like ours at vast distances, each potentially harboring planets, each representing a complete stellar system with its own history and characteristics. The band of the Milky Way stretches across the sky, a river of starlight from the combined glow of billions of stars, too distant to see individually, marking the plane of our galaxy's disk, as seen from our position within it. Other galaxies appear as faint, fuzzy patches, including the Andromeda Galaxy, visible as a small oval smudge in the constellation Andromeda, our nearest large galactic neighbor, containing perhaps 1 trillion stars, located about 2.5 million light-years away, the most distant object visible to the unaided human eye, its light having traveled through space for 2.5 million years before reaching us, showing us Andromeda as it appeared when our ancestors were just beginning to evolve from earlier hominids. When ancient peoples looked at the night sky, they saw the same stars we see today, though arranged in slightly different patterns due to the slow movement of stars in their orbits around the galactic center. And they created constellations, connecting bright stars into imaginary figures that represented animals, heroes, gods, and mythological scenes, stories told in the sky that helped them make sense of their world and pass on cultural knowledge. These constellations, still used today to divide up the sky and identify the positions of celestial objects, remind us of the long history of human observation of the heavens, of our enduring fascination with the cosmos, of the universal human impulse to look up and wonder what is out there and what it all means. For most of human history, the nature of the stars was unknown, their distances uncertain, their composition mysterious. They were simply points of light in the night sky, unchanging and eternal as far as ordinary observation could tell, perhaps attached to a celestial sphere that rotated around Earth, perhaps holes in an opaque barrier through which heavenly fire shone, perhaps the campfires of spirits or gods dwelling in the sky. Only in the last few centuries, and especially in the last 100 years, have we come to understand what stars truly are, how they form and evolve and die, how they produce the energy that makes them shine, how they create the heavy elements that make planets and life possible, how they are organized into galaxies, and how galaxies are organized into the large-scale structure of the universe. This transformation of our understanding, from viewing stars as mysterious lights to understanding them as nuclear furnaces operating on well-known physical principles, represents one of the great intellectual achievements of our species, a triumph of observation and reasoning and mathematical analysis that has revealed the workings of nature at scales far beyond direct human experience. The fact that we can understand stars, that we can calculate what happens in their cores, that we can predict their evolution over billions of years, that we can determine their masses and temperatures and compositions from light that has traveled across vast distances, demonstrates the power of the scientific method and the capacity of the human mind to comprehend even the most remote and extreme phenomena in nature. The elements that make up our world, the carbon in organic molecules, the oxygen we breathe, the iron in our blood, the calcium in our bones, the silicon in rocks, all were created in stars or in supernova explosions through nuclear fusion processes that occurred at temperatures of millions or billions of degrees, in environments far removed from the gentle conditions on Earth's surface where we live. Every time you breathe, you are inhaling atoms that were once inside stars, that were forged in stellar furnaces and blown into space when those stars died, that drifted through the interstellar medium for millions or billions of years before being incorporated into the cloud that formed our solar system, that were present in the disk around the young sun, that became part of Earth, that cycled through the atmosphere and oceans and living things for billions of years before entering your lungs at this moment. This recycling of matter, this continuous flow of atoms, from stars to space, to new stars and planets, to organisms and back again, connects everything in the universe in a web of material relationships that spans cosmic time and space. You are not separate from the universe, but intimately connected to it, not just in an abstract philosophical sense, but in a concrete physical sense, through the atoms you are made of, through the light and heat you receive from the sun, through the gravity that holds you to Earth's surface, through the air you breathe and the water you drink and the food you eat, all of which come ultimately from the matter created in the Big Bang and processed through stars, all of which participate in the ongoing cosmic cycle of creation and destruction and transformation. The scale of the universe, which seems vast and overwhelming when we first encounter it, can also be a source of perspective and tranquility, reminding us that our individual concerns and anxieties, while real and important to us, are small in the cosmic context, that the universe has been unfolding according to physical laws for nearly 14 billion years, without regard to human desires or plans, that it will continue to evolve long after we are gone, that there is something larger than ourselves and our immediate circumstances, something enduring and magnificent that we are privileged to be part of for a brief time. This perspective does not diminish the value of individual human life or suggest that our concerns do not matter, but it can provide a sense of proportion, a reminder that many of the things we worry about are not as significant as they seem in the moment, that there is beauty and wonder in the world beyond our personal dramas and difficulties. Many people find comfort in contemplating the cosmos, in learning about astronomy and cosmology, in looking at images from telescopes, or reading about the latest discoveries, because it takes them out of themselves, shifts their attention from their own problems and preoccupations to something vast and beautiful and awe-inspiring. This sense of awe, which psychological research suggests has beneficial effects on well-being and pro-social behavior, can arise from encountering things that are vast in scale or complex beyond easy comprehension. And few things inspire awe more readily than contemplating the cosmos, with its billions of galaxies, each containing billions of stars, with its timescales of billions of years, with its phenomena like black holes and neutron stars and gamma-ray bursts that operate at extremes of gravity and energy and density far beyond anything in ordinary experience. As we approach the conclusion of our long journey through cosmic space and time, as we have traced the universe from its beginning in the Big Bang, through all the stages of its evolution to the present and forward into the far future, we can reflect on the extraordinary privilege of being alive at this particular moment in cosmic history, when stars still shine brightly, when galaxies are arranged in magnificent structures, when planets orbit their suns in stable configurations that allow for the possibility of life, when the universe is neither too young for complexity to have developed, nor too old for energy to remain available. We live in what might be called the golden age of the universe, after structure has formed, but before it begins to seriously decay, when conditions are optimal for the existence of complex organized systems like living things and conscious beings. This golden age will last for trillions of years by some measures, as long as stars continue to form and shine, but it is still a finite period in the infinite future of the universe, a special time that will eventually give way to the long twilight of the degenerate and black hole eras, when the universe becomes progressively darker and colder and emptier. Future beings, if any exist in those far times, will look back on our era with something like nostalgia, as a time when the universe was young and energetic, when every galaxy contained billions of shining stars, when new stars were being born and supernovae were exploding, and the cosmos was alive with activity. We are fortunate to exist now, in this time of cosmic vitality and abundance, when the universe still retains much of the energy and organization that emerged from the Big Bang, before entropy and expansion have had their full effects. Your own existence, improbable as it is, when you consider all the contingencies that had to occur for you to be here, all the events in cosmic and biological history that had to unfold in exactly the way they did, represents a kind of miracle, not in the sense of violating natural law, but in the sense of being extraordinarily unlikely and precious. The specific arrangement of atoms that makes you who you are has never existed before and will never exist again. And while you share most of your atoms with other humans, and indeed with all life on Earth, while your basic structure and function are determined by genes that have been preserved and passed down through billions of years of evolution, you are nonetheless unique, a singular pattern that appears once in the history of the universe and then dissolves, never to be repeated. This uniqueness applies to every conscious being, every organism, every planet, every star, every galaxy, each one different in its details, even though they may follow similar general patterns and obey the same physical laws. The universe, for all its underlying simplicity and regularity, for all the elegance of the fundamental laws that govern it, produces an inexhaustible diversity and richness in its specific manifestations. No two snowflakes exactly alike, no two stars precisely identical, no two planets sharing the exact same history, no two conscious experiences perfectly matching. This combination of unity and diversity, of simple laws producing complex outcomes, of order and randomness working together, characterizes the cosmos at every scale and represents perhaps the fundamental creative principle of nature. As your breathing continues in its slow, steady rhythm, as your body rests in comfort, and your mind drifts in that quiet space between waking and sleeping, You might imagine yourself floating in space, not the harsh, cold vacuum of actual outer space, but a gentle, supportive emptiness, surrounded by stars that shine with soft, unwavering light, by nebulae glowing in pastel colors, by galaxies spiraling in graceful arcs, all of it silent and peaceful, all of it connected by invisible threads of gravity and electromagnetic radiation, all of it part of one unified cosmos that began in the Big Bang and has been evolving ever since, following its trajectory through time according to the laws of physics, creating and destroying structure in an eternal cosmic dance. The silence of space, the absence of sound because there is no air to carry vibrations, might seem lonely or eerie, but it can also feel peaceful, a profound quiet deeper than any earthly silence, where the only vibrations are light waves and gravitational waves carrying information across vast distances at finite but immense speeds, where the pace of change is usually slow and gentle, stars burning steadily for billions of years, galaxies rotating over hundreds of millions of years, the universe expanding continuously, but not so fast that you would notice it over human timescales. This is cosmic time, so different from the hurried pace of modern human life, operating on scales where 1,000,000 years is brief, where patience is measured in eons, where there is no rush because there is all the time in the universe, literally. In this cosmic perspective, in this vast context of space and time, your own concerns and worries and anxieties begin to seem smaller, more manageable, less overwhelming. The universe does not judge you or demand anything of you, does not care whether you succeed or fail by human standards, simply holds you in its immense embrace as one small part of its ongoing evolution, one temporary pattern among countless others. This can be liberating, freeing you from the pressure to be anything other than what you are, allowing you to simply exist, to breathe, to rest, to let go of the constant striving and effort that characterizes so much of waking life, to surrender to the natural rhythms of your body and the gentle pull of sleep that comes when you stop resisting and allow yourself to drift. Sleep, that daily journey into unconsciousness, that necessary pause in awareness, that surrender of conscious control, is as natural and fundamental as anything in the universe. A biological rhythm that has evolved over hundreds of millions of years, shared by creatures from insects to mammals, essential for health and well-being, allowing the brain to consolidate memories and clear metabolic waste, allowing the body to repair and restore itself, allowing consciousness to temporarily cease monitoring and processing of information and simply rest. We spend about 1/3 of our lives sleeping, and while this might seem like time lost or wasted from the perspective of conscious activity, it is actually time invested in maintaining the systems that make consciousness possible, time that is as valuable and necessary as waking time, even though we are not aware of it in the usual sense. The transition from waking to sleeping, from full conscious awareness to the reduced awareness of drowsiness, to the altered consciousness of dreaming, to the complete unconsciousness of deep sleep, occurs gradually and naturally when conditions are right, when the body is relaxed, when the environment is calm and comfortable, when the mind is not actively engaged in problem-solving or worrying, when you allow yourself to let go of control and trust in the natural process. You cannot force sleep to come, but you can create conditions that encourage it, can allow your body to relax completely, can let your breathing slow and deepen, can allow your thoughts to drift without following them or trying to control them, can simply rest in the present moment without effort or intention, and sleep will come on its own, in its own time, as naturally as the expansion of the universe or the shining of stars. As we come very gently toward the end of our long cosmic journey, as the story of the universe from the Big Bang to the far future approaches its conclusion, know that you have traveled through nearly 14 billion years of history, have witnessed the birth of space and time, have seen particles and atoms form, have watched the first stars ignite and the first galaxies assemble, have traced the evolution of structure over cosmic time, have arrived at the present moment where you exist as a conscious being in a vast and ancient cosmos, aware of yourself and your surroundings, capable of understanding the story of your own origins, made of atoms forged in stars, animated by energy from the sun, held to earth by gravity, breathing air, your heart beating in a rhythm that has continued without pause since you were born and will continue until you die, your brain processing information, your consciousness experiencing this moment, this now, this present that is all that truly exists. And as you rest here, as your body grows heavier and more relaxed, as your breathing slows and deepens, as your mind becomes quieter and begins to drift, you can let yourself sink into the embrace of the cosmos. Let the vastness of space and time hold you gently. Let the knowledge that you are part of this grand cosmic story comfort you. Let the understanding that everything that exists is connected through an unbroken chain of causation going back to the beginning give you peace. You are exactly where you belong, a child of the universe, a temporary flowering of cosmic evolution, here for a brief time to experience and observe and understand, and then returning your constituent atoms to the cosmic cycle, contributing your small part to the ongoing story that will continue long after you are gone. The universe asks nothing of you except to exist, to be what you are, and in this moment, what you are is a being at rest, breathing softly, drifting towards sleep, held safely by forces beyond your control and beyond your need to understand or manage. Simply here, simply present, simply being. There is nothing you need to do, nowhere you need to go, nothing you need to figure out or solve or fix. Just this moment of rest, this gentle floating in the vast ocean of cosmic time, this peaceful surrender to the natural rhythms that govern all things, from the quantum fluctuations at the smallest scales to the expansion of the universe at the largest scales, everything flowing and changing and evolving according to laws that ensure nothing lasts forever, but also ensure that everything is precisely as it should be in each moment. Let your eyes remain closed now, heavy and comfortable. No need to open them, no need to see anything or do anything. Just resting in darkness that is peaceful and safe. A darkness like the darkness of space, but warmer and softer. A darkness that holds you and comforts you. A darkness that is not empty, but full of potential, like the quantum vacuum from which the universe itself emerged, like the cosmic dark ages before the first stars, like the gentle night that covers Earth when your part of the planet turns away from the sun. A natural darkness that brings rest and renewal, that allows dreams to come, that marks the boundary between waking and sleeping. Your breathing has become very slow now, very gentle, like waves lapping softly on a shore, like the slow expansion of the universe itself. Each breath taking you deeper into relaxation, each exhalation releasing any remaining tension, any lingering thoughts, any sense of effort or strain, leaving only peace, only quiet, only the gentle awareness of being alive in this moment, this present, this now that is eternal, even though it constantly becomes the past, giving way to a new now and another, in an endless flow that is time itself, that is change itself, that is the very essence of existence, in a universe that began with the Big Bang and has been evolving ever since, unfolding its possibilities, exploring its potential, creating structure and beauty and complexity and consciousness. And now, in this moment, allowing you to rest. Sleep comes like the darkness between stars, like the silence of space, like the patience of cosmic time, inevitable and natural, requiring no effort, no struggle, no attempt to force or control, simply arriving when conditions are right, gently taking your consciousness and transforming it, carrying you into dreams or into deep sleep, into that necessary period of rest that renews and restores, that allows tomorrow to begin fresh, that is as essential to life as breathing or eating or any other biological process, that connects you, every sleeping creature that has ever existed, every organism that has ever closed its eyes or ceased its activity and allowed itself to rest, going back billions of years to the first living things that developed circadian rhythms, going forward to whatever living things might exist in the distant future, all part of the same cosmic story, all made of the same stellar material, all subject to the same physical laws, all temporary patterns in the eternal flow of the universe. And so, as the story of the cosmos completes its long arc, as we have traveled together from the beginning of time to this present moment, and glimpse the far future that stretches ahead, you can let yourself drift now. Let yourself float in that peaceful space between waking and sleeping, trusting in the universe to hold you, trusting in your body to rest and restore itself, trusting in the natural process of sleep to come and do its work, with no need for effort or concern, just gentle, peaceful drift into darkness and dreams, into rest and renewal, into the quiet depths of sleep, where consciousness temporarily ceases and the cosmos continues its ancient dance. Galaxies turning, stars shining, planets orbiting, atoms vibrating, and you resting peacefully, breathing softly, sleeping deeply, held safely in the infinite embrace of space and time, part of everything, connected to everything, at peace in the vast and beautiful universe that is your home, now and always, as you drift deeper, deeper into restful, peaceful, deep and healing sleep. The cosmic dance continues, eternal and patient, while you rest in perfect peace, your consciousness dissolving like morning mist, your awareness fading like starlight at dawn, your thoughts becoming softer, quieter, more distant, like echoes from across the universe, growing fainter and fainter until they are gone completely, leaving only deep, profound, peaceful rest. The atoms of your body remain, vibrating gently with thermal energy, held together by electromagnetic forces that have operated unchanged since the first atoms formed hundreds of thousands of years after the Big Bang. But your awareness of them fades, your sense of self dissolves, and you become simply part of the universe again. Not separate, not distinct, just matter and energy arranged in a particular pattern, resting, regenerating, dreaming perhaps, or sinking into dreamless sleep, that deepest rest where even dreams do not come, where there is only darkness and peace, and the slow, steady rhythm of breathing and heartbeat, automatic processes that continue without conscious guidance, allowing you to rest completely, to let go completely, to sleep completely. The universe holds you as it holds everything, with gravity and electromagnetic forces, with the fabric of space-time itself, curved gently by Earth's mass, keeping you safely on the surface of this planet as it spins through space at hundreds of kilometers per second, orbiting the Sun, which orbits the galactic center, which moves through intergalactic space. All of this vast motion, unfelt by you as you rest in stillness, in peace, in the deep quietude of sleep that comes now, like nightfall, like the cooling of the early universe, like the gentle expansion of space itself, inevitable, natural, requiring nothing from you, asking nothing of you, simply enfolding you in its embrace. And in this final moment of awareness, before sleep takes you completely, before consciousness fades entirely, and you surrender to the deep rest your body needs, you might feel a sense of gratitude, a quiet appreciation for this existence, however brief and improbable, for this opportunity to have experienced the universe from within, to have been a conscious part of the cosmos for a time, to have looked up at the stars and wondered, to have learned the story of where you came from and where everything came from, to have understood, even if only partially, the magnificent universe that is your home. This moment of being alive, of breathing, of existing, is a gift from the cosmos to itself. And now you can rest in that knowledge. Let it settle over you like a soft blanket, warm and comforting as you drift into sleep, into dreams, into the peaceful darkness where rest and renewal await. Sleep now, gently, peacefully, deeply, held by the universe that created you, part of the eternal cosmic story, safe and protected, breathing softly in the endless night, your consciousness dimming like a star whose light finally reaches its end, fading gradually, gently, beautifully, until there is only darkness, only peace, only the infinite stillness of deep and restful sleep, where you can remain for as long as your body needs, dreaming the dreams that come from the depths of the mind, or resting in dreamless peace. Either way, perfectly safe, perfectly at rest, perfectly held in the embrace of space and time, in the heart of the cosmos, at home in the universe, sleeping peacefully now, so peacefully, so deeply, so completely. As the stars continue their silent watch, as galaxies spiral through the darkness, as the universe expands gently outward, and you, precious and temporary and perfect, rest in the eternal now, breathing softly, sleeping deeply, at peace. Good night.